took an early break yesterday. Didn't get a lot of time in. The game plan today is to stream for at least 3 hours. And then I might take a break for dinner and then stream for another couple hours. Okay. So let's pop open our terminal, open up our downloads. Actually, no, I don't want to do it from here. Let's go to downloads here. I did an upgrade on my Marchi, so I can yeah, I got this new theme I like. So what was I doing? Okay, I think we left off on representing strings. So let's just read through that real quick. A string in C is encoded by an array of characters terminated by null, having value 0 character. Each character is represented by some standard encoding, with the most common being ASCII character code. Thus, if we run our routine show bytes with arguments 1, 2, 3, 4, 5, and 6 to include a terminating character, we get the result so and so. Observe that the ASCII code for the decimal digit x happens to be 0x3x. 1, 2, 3, 4, 5, and that would be and that the terminating byte has the hex representation 0, 0. This same result would be obtained on any system using ASCII and character code independent byte ordering and word size conventions. As a consequence, text data are more platform independent than binary data. Alright, so then we came to this practice problem. We already read that part, so let's jump to CSAPP, CD chapter 02. Sorry, CD chapter 02. If I can type correctly here. There we go. Let's open up problems. Yeah. Oh, now Vim needs to update. Okay. So down here we have 2.7. And we'll just bring that center screen. It says, what would be printed as a result of the following call to show bytes? Okay. The stir len, I believe, excludes the null byte. So I'm going to say the output would be the character of M, N, O, P, Q, R, but no null byte. So that would be M. If we do over here, man ASCII, and then we just go down to character M, which is here. So we want lowercase m here, which is 100. Decimal? That'd be decimal. Hexadecimal would be M here, which would be 6D. And we can confirm that with Python. If we say char of 0x6D, it's M. So it's going to be 6D. N is 6E. O is 6F. P is 7, 0. Q is 7, 1. And R is 7, 2. Oops. 7, 2. And I'll just throw it there, and then we can check our answer here real quick. $60, 6E, 6F, 70, 7172. Recall the library function certainly does not count the term null character, so show bytes printed only through the character R. Yep. So now we go to continue reading. You know I'm going to do that. I'm going to say get status, get add all, get PC. Oh, we got stuff here with A, B, C, D, A. Need to fix those. Chapter 02 problems. We're going to search for space, new line. Sorry, new line. I think it's R, right? There we go. Page through everything. Looks good. Good CI. So progress on chapter 02. Come on, what are you doing here? There we go. Okay. Let's continue reading. Representing code considering the following C function. So we have a sum function returns an integer, takes in two integers as arguments, and returns the sum of the two. When compiled on our sample machines, we generate machine code having the following representations. So on Linux and Windows, it's nearly identical for 32-bit. We differ only by the second to last byte. And then Windows is similar, but it's offset a little bit. Yeah, similar encodings but offset. Sun is completely different, of course. You gotta be completely different. It says here we find that the instruction codings are different. Different machine types use different and incompatible instructions and encodings. Even identical processors running different operating systems have differences in their coding conventions or calling conventions. And hence are not binary compatible. So binary code is seldom portable across different combinations of machines and operating systems. A fundamental concept of computer systems is that a program, from the perspective of the machine, is simply a sequence of bytes. The machine has no information about the original source program, except perhaps some auxiliary tables maintained to aid in debugging. We will see this more clearly when we study machine-level programming in Chapter 3. Yay! Introduction to Boolean. Actually, before we go on, let's continue to the aside about Unicode. So it says the Unicode standard for text encoding, the ASCII character set is suitable for encoding English language documents, but it does not have much in the way of special characters, such as the French weird C. It is wholly unsuited for encoding documents in languages such as Greek, Russian, and Chinese. For over the years, a variety of methods have been developed to encode text for different languages. The Unicode Consortium has devised the most comprehensive and widely accepted standard for encoding text. The current Unicode standard, comprehensive and widely accepted. The Unicode standard version 7 has a repertoire of over 100,000 characters, supporting a wide range of languages, including the ancient languages of Egypt and Babylon. To their credit, the Unicode Technical Committee rejected a proposal to include a standard writing for Klingon, a fictional civilization from the television series Star Trek. To their credit. That's funny, this is to their credit. Author is adding moral judgment about Star Trek fans. The base encoding, known as the Universal Character Set or Unicode, uses a 32-bit representation of characters. So 4 times as large as ASCII, or more than 4 times. This would seem to require every string of text consists of 4 bytes per character. However, alternative encodings are possible. where common characters require just 1 or 2 bytes, while less common ones require more. In particular, the UTF-8 representation encodes each character as a sequence of bytes, such that the standard ASCII characters use the same single byte encodings as they have in ASCII, implying that all ASCII byte sequences have the same meaning in UTF-8 as they do in ASCII. The Java programming language uses Unicode in its representation of strings. Program libraries are also available for C to support Unicode. All right, introduction to Boolean algebra. Since binary values are at the core of how computers encode, store, and manipulate information, a rich body of mathematical knowledge has evolved around the study of the values 0 and 1. This started with the work of George Boole in 1815 to 1864. Around 1850, sorry, that was his lifespan, around 1850, and is thus known as Boolean algebra. Boole observed that by encoding logical values true and false as binary values 1 and 0, he could formulate an algebra that captured the basic principles of logical reasoning. The simplest Boolean algebra is defined over the two-element set 0 and 1. Figure 2.7 defines several operations in this algebra. Our symbols for representing these operations are chosen to match those used by the C-bit level operations. What's going on here? Give me 1 second. I messed up my chat. There we go. Okay, so we got our operations for Boolean algebra. So the first one is negation. Second one is AND. These are just truth tables. Second one is OR. Last one is XOR. So C-bit level operations, as we discussed later. The Boolean operator tilde corresponds to the logical operation not, denoted by the symbol so-and-so. That is, we say that not P is true when P is not true, and vice versa. Correspondingly, not P equals 1 when P equals 0, and vice versa. Boolean operation and the Boolean operation AND, or ampersand, corresponds to the logical operation AND, denoted by the symbol caret. This is where things get weird, because caret is also an XOR operator. We say P and Q holds when both P is true and Q is true. Correspondingly, P and ampersand Q equals 1 only when P is equal to 1 and Q is equal to 1, or is truthy. Boolean greater than 0, you should say. Boolean operation OR corresponds to the logical operation OR, denoted by the symbol V. We say that P v Q holds when either P is true or Q is true. Correspondingly, P or Q equals 1 when either P is 1 or Q is 1. Boolean operation caret corresponds to the logical operation exclusive OR, denoted by a symbol 0, the plus sign inside of it, because it's kind of like plus. If you think about it, Boolean addition. So this is 0 plus 0 would be 0. 0 plus 1 would be 1. 0 plus 1 would be 1. And 1 plus 1 would be 0 with a carry bit. So it's kind of like plus addition. XOR is addition with a carry bit. Okay. We say that P XOR Q holds when either P is true or Q is true, but not both. Correspondingly, P caret Q equals 1 when either P is equal 1 and Q is equal to 0, or P is equal to 0 and Q is equal to 1. Claude Shannon, who later founded the field of information theory, first made the connection between Boolean algebra and digital logic. In his 1937 master's thesis, he showed that Boolean algebra could be applied to the design. I'm going to highlight Claude Shannon because I'm not familiar with him. He showed that Boolean algebra could be applied to the design and analysis of networks of electromechanical relays. Although computer technology has advanced considerably since, Boolean algebra still plays a central role in the design and analysis of digital systems. We can extend our 4 Boolean operations to also operate on bit vectors, strings of zeros and ones of some fixed length W. We define the operations over bit vectors according to their applications to the matching elements of the arguments. Let A and B denote bit vectors A w-1 to A0 and B w-1 to B0 respectively. We define A and B to also be a bit vector of length W, where the we define A and B to also be a bit vector of length W, where the ith element equals A sub I and B sub I. For 0 is less than or equal to I, and it's less than W. Okay. Yep. The operations or, caret, and tilde are extended to bit vectors in a similar fashion. As examples, consider the case where W is equal to 4 with the arguments A is equal to 0, 1, 1, 0, and B is equal to 1, 1, 0, 0. Then the four operations A and B, A or B, AX or B, and not B yield the so-and-so values. Fill in the following table showing the results of evaluating Boolean operations on bit vectors. So it's going to involve some type of table thing. Let's see it into chapter 02, Vim up our problems. And we'll go down to the bottom here and say, hey, you're at 2.8 now, bro. And 2.8 involves a table. So we'll go ahead and we'll just copy the table here. I don't need to generate another markdown table. So this is going to be operation and result. So we'll just say op and result. And we'll just go down here. In fact, I'll just delete everything in here like that. We'll do the same thing here. I'll do that, and then in here I'll just say, hey, oops, replace with space, and you actually need to have an additional one here like that. 1, 2, 3, 4, 5, 6. So that's going to need 6. 1, 2, 3, 4, 5, 6. Bam. So now we delete this stuff. Okay. So our operation so we have A, B, tilde, A, tilde, B, A and B, A and B. So that means we're going to need another element here. Let's go ahead and do that. Oops. Oops. Go away, please. There we go. You need to go there. You need to go here. Great. Okay. So we got A and B. A. Oops. We just have 3 operations here, which is AND, OR, and XOR. Okay, so A we already have, which is 2, 3, 4, 5, 6, 7, 8. So we need 2, I think. So 1, 2, 3, 4, 5, 6, 7, 8, correct. This will be 0, 1, 0, 0, 1, 1, 1, 0. And then this next one is going to be correct 1, 1, 1, 0, 0, 0, 0, 1. And I like spacing these things out a little bit. Let's do that, why not? So you got 2 there and 1, 2, 3 there. And then we'll just do bam. And then here we're gonna have not A, which would be 1, 0, 1, 1, 0, 0, 0, 1. And then we'll have not B, which is 0, 0, 0, 1, 1, 1, 1, 0. And then we'll have A and B, which is going to be 0, 1, 0, 0, 0, 0, 0, 0. And then we'll have A or B, which is going to be 1, 1, 1, 0, 1, 1, 1, 1. And then we're going to have A XOR B, which is 1, 0, 1, 0, 1, 1, 1, 1. Cool. It's pretty easy, straightforward problem. Let's check our answer key here. So obviously these values we already got. Next thing is going to be 1011, 101, 0001. Yep. 0001, 1110. Yep. And then this is going to be just 1 bit there. Yep. And then we have 1 bit unset there. Yep. And then we have those two. Cool. Not hard. Alright, let's continue on with the reading. I guess we can do this web-aside. Do you want to do the web-aside? Let's check it out. Web-aside. The Boolean operations or and not operating on bit vectors of length w form a Boolean algebra for any integer w greater than 0. The simplest is the case where w is equal to 1. And there are just 2 elements, but for the more general case where there are 2 to the w bit vectors of length w. Boolean algebra has many of the same properties as arithmetic over integers. For example, just as multiplication distributes over addition, written as a times b plus c and is equal to a times b plus a times c, Boolean operation and ampersand distributes over or, written as a and bc is equal to a and b or a and c. In addition, however, Boolean operation or distributes over and so we can write a or bc is equal to a or b and a or c, whereas we cannot say that a plus bc is equal to a plus b times a plus c holds for all integers. When we consider operations XOR and not operating on bit vectors like W, we get a different mathematical form known as a Boolean ring. Boolean rings have many properties in common with integer arithmetic. I'm going to highlight Boolean ring because I'm not familiar with that term. Common with Boolean rings have many properties in common with integer arithmetic. For example, one property of integer arithmetic is that every value x has an additive inverse negative x, such that x plus minus x is equal to 0. A similar property holds true for Boolean rings, where XOR is the addition operation, but in this case, each element is its own additive inverse. That is, a or XOR a is equal to 0. For any value a, where we use 0, they're here to represent a bit vector of all zeros. We can see this holds for single bits since 0 XOR 0 is equal to 1, XOR 1, which is equal to 0. And it extends to bit vectors as well. This property holds even when we rearrange terms and combine them in different order. And so A XOR B XOR A is equal to B. This property leads to some interesting results and clever tricks, as we'll explore in problem 210. Let's pull up the web-aside. Please go away, thank you. And this is going to be CSAPP, web-asides, data bool. Okay, so this is like a 6-page thing. And how many web-asides are there? We'll say mkdir AS01. Let's go into there. Actually, you know what? Let's do rmdir AS01. CD into chapter 02. And in here we're just going to say aside ASIDE bool, data bool dot md, mv aside, sorry, let's vim up aside as underscore data underscore bool dot md. There we go. And then here I'll just hide this thing, and we will send that to 2 for now, just so we can zoom in on this a little bit. There we go. And we'll zoom out 1. Okay. More on Boolean algebra and Boolean rings. Notice the material in this document is supplementary material to the book Computer Systems, a Programmer's Perspective 3rd edition. Blah, blah, blah. This document is being made available to public. Subject to copyright provisions, you're free to copy and distribute it, but you must give attribution for any use of this material. Motivation, since binary values are at the core of how computers encode, store, and manipulate information. A rich body of mathematical knowledge has evolved around the study of values 0 and 1. This started with the work of George Boole. Boole observed that the encoding logical values true and false. Formula, we already discussed this. We don't need to discuss it again. From logic to algebra, there is an infinite number of Boolean algebras, where the simplest is defined over the 2 element set 0 and 1. Figure 1 defines several operations in this Boolean algebra, or symbols for representing these operations, chosen to match those by C bit level operations. As we will discuss later, the Boolean operator tilde corresponds to logical operation not, denoted in the propositional logic as that little thing. That is, we say that not P is true, and I already read this. I'm not reading this again. Claude Shannon, who later found the field of information theory, first made a connection. Okay, we already talked about that. Okay, so we want to start with properties of Boolean algebras and rings. There are many parallels between integer arithmetic and Boolean algebras, as well as several differences. In particular, the set of integers denoted z forms a mathematical structure known as a ring, denoted z plus x minus 0, 1. Huh? Denoted, so that's a ring. With addition serving as a sum operation, multiplication serving as a product operation, negation serving as the inverse, and element 0, 1 serving as the additive and multiplicative identities. The Boolean algebra 0, 1 and not 0, 1 has similar properties. Figure 2 highlights properties of these 2 structures, showing the properties that are common to both and those that are unique to one or the other. One important difference is that not A is not an inverse for A under OR. Are there like problems with this, or is this just like additional reading? I think it's just additional reading. Okay. They just didn't want to go into super detail on Boolean algebra. Okay. What good is abstract algebra? Abstract algebra involves identifying and analyzing the common properties of mathematical operations in different domains. Typically, the algebra is characterized by a set of elements, some of its key operations, and some important elements. As an example, modular arithmetic also forms a ring. For modulus n, the algebra is denoted zm plus n xn minus n 0, 1, with components defined as the following. Even though modular arithmetic yields different results from integer arithmetic, it has many of the same mathematical properties. Other well-known rings include rational and real numbers. Share properties unique to rings, the inverse, unique to Boolean algebras. Two mathematical structures share many properties, but there are key differences, particularly between negation and subtraction. If we replace the OR operation of Boolean algebra by the exclusive OR operation and the complement operation with the identity operation I, where I of A is equal to A for all A, we have the structure. So the structure is no longer a Boolean algebra. In fact, it's a ring. It can be a particularly simple form of a ring consisting of all integers, with both addition and multiplication performed modulo n. In this case, we have n is equal to 2. That is, the Boolean and exclusive OR operands correspond to multiplication and addition modulo 2. One curious property of this algebra is that every element is its own additive inverse. Aside, who besides mathematicians care about Boolean rings? Every time you enjoy the clarity of music recorded on a CD or the quality of video recorded on DVD, you are taking advantage of Boolean rings. These technologies rely on error correcting codes to reliably retrieve the bits from a disk even when dirt and scratches are present. The mathematical basis for error correcting codes is a linear algebra based on Boolean rings. General forms of Boolean algebra and rings. We can extend the 4 Boolean operations to also operate on bit vectors, i.e. strings of zeros and ones of some fixed length W. We can extend the 4 Boolean operations to also operate on bit vectors, strings of zeros and one of some fixed length W. Define the operations over bit vectors according to the application to the matching elements of the arguments. Let A and B denote the bit vectors so and so, respectively. We define A and B to also be a bit vector of length W. To express this generalization in algebraic terms, let 0, 1, W denote the set of all strings of 0 and 1s having length W, and A super W denote all the string consisting of W repetitions of symbol A. Then one can see that the resulting algebras from Boolean algebra form Boolean algebras and rings respectively. Each value of W defines a different Boolean algebra and a different Boolean ring. Aside, are Boolean rings the same as modular arithmetic? The 2-element Boolean ring is identical to the ring of integers modulo 2. The generalization of bit vectors of length W, however, yields a very different ring from modular arithmetic. Representing and manipulating sets. One useful application of bit vectors is to replace finite sets. We can encode any subset A subset of so-and-so with bit vector so-and-so, where A sub I is equal to 1 if and only if I is an element of A. For example, recalling that we write AW minus 1 on the left hand side and A0 on the right, bit vector so and so encodes the set 0, 3, 5, 6. This is important. One useful application of bit vectors is to represent finite sets. We can encode any subset A, which is a subset of 0, 1 up to W minus 1. So if you have like 64 bits, say, then you can record 0 to 63 with a bit vector. Yeah. So you got 0, 1, 2, 3, 4, 5, 6. Yeah. So you just set bits for the positions that you want to encode. That's not crazy. You just OR them together. OR would be a set union operation. Bit vector B is equal to that. Encodes, let's see, we got 0, 2, 4, 6. Yep. With this way of encoding bits, Boolean operations, or an ampersand corresponding to the set union and intersection, respectively, and not corresponding to set complement. Continue our earlier example, the operation A and B yields bit vector so-and-so, while A union B is 0, 6. Yeah, okay. Yep. Or A intersection union 6, and the exclusive OR would be the symmetric difference. In fact, for the set S, the structure P sub S union intersection, I don't know what that operator is, null set, and S itself forms a Boolean algebra where P of S denotes the set of all subsets S, and the high bar denotes the set complement operator. That is, for any set A, its complement is the set bar A, which is equal to A is element of S, A is not element of A. Okay. The ability to represent and manipulate finite sets using bit vectors operations is a practical outcome of a deep mathematical principle. Ugh. I guess the mathematics is kind of lost on me a little bit. I mean, if you told me, hey, I want you to represent a set, like this is something that I would rationally just come to, that you would have bit positions for all the numeric values of that set up to the length of the amount of bits that you have. So if you have 64 bits, you can say there's up to, if your range is 0 to 63, you could have anything in that range. Yeah, I guess it seems, completely obvious that you would do that. Alright, so that concludes the website. So we'll just mark that as done there. Okay, let's continue onwards. So I did this problem. Zoom out a little bit. Alright, so if I hit 0, what does that do? Oh, that's too far. Okay, so that's about a page. Can I go one more in? No. Oh, you can flip things? What? Okay, well that's where we're at. Okay, one useful application of bit vectors is to represent finite sets. We already talked about this in the aside. We can encode any subset A is a subset. Yeah, I'm gonna skip past this. We will see the encoding of sets by bit vectors in a number of practical applications. For example, in chapter 8, we will see that there are a number of different signals that can interpret the execution of a program. We can selectively enable or disable different signals by specifying a bit vector mask, where 1 in the bit position I indicates that the signal I is enabled and a 0 indicates that it's disabled. Thus, the mask represents the set of enabled signals. That's why there's only 32 signals, like unreliable signals. What do they call them? Non-real-time signals. Because there were only 32 bits on the systems back then. Okay, computers generate color pictures on a video screen or a liquid crystal display by mixing 3 different colors of light: red, green, and blue. Imagine a simple scheme with 3 different lights, each of which can be turned on or off, projecting onto the glass screen. Okay. We can then create 8 different colors based on the absence or presence of the light source RGB. Yeah. Each of these colors can be represented as a bit vector of length 3, and we can apply Boolean operations to them. The complement, so this is the problem, I guess. Go down to here and say 2.9. So the problem, so it's going to be sub A, sub B, sub problem A. The complement of a color is formed by turning off the lights that are on, and turning on the lights that are off. What would the complement of each of the 8 colors listed above be? Okay, let's grab a table here. Okay, so we got RGB and color. So we'll just do R, and we'll subtract away all of these. And then here, I'll just put zeros. And then we'll do the same thing here. Subtract away RG. And we can do 3, 4, 5, 6, 7, 8. Okay. Now we can copy everything from here and paste it there. Say B, and then the resulting color. Oops. My bad, my bad. Color. Okay. So this is the truth table. We gotta do our ones over here. going to be split up here to be like this. And then this is going to be split up like this. Okay. So this is obviously going to be black. Block. Black. Come on. Blue. Green. Cyan. Red. Magenta. Yellow. White. So we gotta go there. Okay. So then it wants to say do the complements of these. Which would be the tilde color. And we're probably gonna need one there, if I'm not mistaken. Which might be better off like that. No. Okay. So black complement would be white, and white's complement would be black. And then blue's complement would be yellow. And yellow's complement would be blue. And green's complement would be 101, which would be magenta. And magentas would be green. And cyan would be red. And red would be cyan. Oops. Cyan. There we go. There we go. Yeah, this is where I was saying it might be better, like, if we did that. I don't know, kind of looks better that way, I think. Okay. Describe the effect of applying Boolean operations on the following colors. Blue or green. So that's going to take blue and green here. So let's add them together. Cyan. Blue or green equals cyan. Yep. Yellow and cyan. So it's cyan and yellow there. Well, it's going to be 0, 1, 0, which is green. And then finally red XOR magenta. So we got red and we got magenta. Exclusive OR, so it'll be 0, 0, 1, should be blue. Oops. Okay. Let's go and check our problem here, which is 2, 9 now. 2, 9. So we already did that. 2, 8, 2, 9. Is that even in here? Oh, did I skip a page? There we go. This problem illustrates how Boolean algebra can be used to describe and reason about real-world systems. We can use that color algebra. We can see that this color algebra is identical to the Boolean algebra over bit vectors length 3. Colors are complemented by complementing the values of red, green, and blue. From this, we can see that white is the complement of black, yellow is the complement of blue, magenta is the complement of green, and cyan is the complement of red. So we got white and black, yellow and blue, magenta and green, and red and cyan. Yep. We perform Boolean operations based on bit vector representations of the colors, which should result in cyan, green, blue. Yep. Okay. Pretty simple stuff. Okay, bit operations in C. Bit level operations in C. One useful feature of C is that it supports bitwise Boolean operations. In fact, the symbols we have used for the Boolean operations are exactly those used by C. Pipe for or, ampersand for and, tilde for not, and caret for exclusive or. These can be applied to any integral data type, including all of those listed in figure 2.3. Here are some examples of expressions evaluating the data type char. As our example shows, the best way to determine the effect of a bit level expression is to expand the hexadecimal arguments to their binary representations, perform the operations in binary, and then convert back to hexadecimal. Okay, practice problem 210. So now we're already on 210. 2.10. There's lots of problems in this book. Maybe I should do the reading first and then do the problems selectively, because there's just so many freaking problems. It would be nice to not do stop and go type thing. It would require me to do some rereading, I think. But I think I'd just feel better doing that, because I'd make more progress on the reading. I don't know. I'm kind of torn what I should do. If I should just do the reading, come back to the problems, do the problems in bulk, or do the problems as I read. Let's ask AI. I'm reading CSAPP book. It has, let's do another sentence. It has a lot of problems throughout the chapters. Should I do the reading first, then come back to the problems? I feel like this really slows down the reading. What does the internet recommend with this specific book? Computer systems, a programmer's perspective. Do problems as you go. The authors explicitly recommend working the practice problems immediately after sections where they appear to test your understanding. I think they said that in the preface. That's the reason why I asked AI, because I didn't want it to go and find that in the preface again. And then checking solutions at the end of the chapter before moving on. Each chapter also has homework problems of varying difficulty. This is part of their pedagogy. They don't expect you to just read text passively. So their intention is clear: read plus immediate practice, not read the whole book first and only doing problems later. Many readers do find CSAPP hard because of the problems. People online describe exactly what you're feeling. The practice and homework problems are where the real learning happens, and they do slow you down. Others also say it's normal to take a long time on them, especially at first, and that trying to work through them is part of internalizing the system's level material. This isn't a sign that you're doing something wrong. The book is meant to be deep and a bit of a grind, especially the exercises. Practical strategy people recommend. Let me move back my desk here because the light is shining in from outside. All right. Option A, balance recommended for most. Read actively. Read a section or small chunk. Try to solve the practice problems immediately. If stuck, review the section again or skim the rest of the chapter, then continue on to the next section reading. This keeps learning solid without dragging you too far ahead, only to forget earlier content. Option B, focus on the narrative first, problems later. If you just want a high level of understanding first for an overview syllabus prep, no. Hybrid method. Okay, that's and the author's intention is to do the problems as he goes, so we'll do that. Okay, so we have, as an application of the property that A XOR A is equal to 0, for any bit vector A, consider the following program: in place swap. So this is the XOR swap, which is a fun way to do a swap. As the name implies, we claim that the effect of this procedure is to swap the values stored at the locations denoted by pointer variables x and y. Note that unlike the usual technique for swapping two values, we do not need a third location to temporarily store one value while we are moving the other. There is no performance advantage to this way of swapping. It is merely an intellectual amusement. Starting with values A and B in the locations pointed to by X and Y respectively. Fill in the table that follows. Given the values, so let's copy a little table here. Our first thing is step. This will be star X. This will be star Y. And then we don't want the rest. So we're dropping two columns there. Oops. Same thing here. There we go. So this is going to be initially. Step 1. I'll just say it's init. 1, 2, 3. Boom, boom, boom. Okay. Okay, and then this is going to be what? What do we want to put here? A and B. Okay, and then these go here. And B, A and B, step 1. Okay, we have X and Y, so this is going to be X or Y. So this will be A. X will still point at A, we're not modifying it. So Y will point to A, X, or B. And then here X will now point to A, X, or B, X, or A. Just be B, A, X, or B. Just to stay B here, and now you modify Y to be A. Okay. Practice problem 210. There you go. This procedure relies on the fact that exclusive OR is commutative and associative, and that A X or A is equal to 0 for any A. So it goes AB, and then AX or B, and then B AX or B, and then B A. Okay, 211. I already knew about the XOR swap trick. I'll learn that from TS Coding. Okay, practice problem 211. Armed with the function in-place swap from 210, you decide to write code that will reverse the elements of an array by swapping elements from opposite ends of the array, working towards the middle. You arrive at the following function. Reverse away int a array in the count. So you say first is equal to 0, last is equal to count minus 1. While first is less than or equal to last, we increment first and reduce last. And then we do an in-place swap between a first and a last. Make sense? When you apply your function to an array containing elements 1, 2, 3, 4, you find the array now has, as expected, elements 4, 3, 2, 1. When you try it on an array with elements 1, 2, 3, 4, 5, however, you're surprised to see that the array now has 5, 4, 0, 2, 1. In fact, you discover that the code always works correctly on arrays of even length, but it sets the middle element to 0 whenever the array is odd length. My guess there would be that to say we have 7, 7. 7 XOR 7 would be 0. So we'd have 7, 0. And then we would perform our operation, say 7 XOR 0. Should be 7, 0. I would think that would work. For an array of odd length, count is 2k plus 1. What are the values of variables first and last? Oh, so you can't do it in the middle array because they're pointing to the same location. It doesn't have to do with their values. It has to do with you're mutating the same place. For an array of odd length, what are the values of variables first and last in the final iteration? Well, let's go ahead and just answer these questions. So count is equal to 2k plus 1. What are the values of variables first and last in the final iteration of the function reverse array? So if in this case it'd be 5. So just do it by example. So we have 5 would be 2 times 2 plus 1. So k would be 2 in that case. So it'd be k plus 1. Let's do 1 for 7. So 7 would be 2, 3 plus 1, which would be 4. Yep. So it's k plus 1. B. Why does this call to function in place swap set there? Because each operation is mutating the same memory address. Yeah. See. So when you assign to star y on step 1, you are actually mutating both star y and star x. The same applies to the other steps. Alright, see what simple modification to the code for reverse array would eliminate this problem? Remove the equal sign from the comparison from the first less than equal last loop condition. Okay, let's check the solution here. 211. The problem illustrates a subtle and interesting feature of our in-place swap routine. Both first and last have the value k, so we're attempting to swap the middle element. I thought it was k plus 1. Oh, this has to do with like indices. It's -1 because, yeah. It would be k plus 1 if we were counting from 1 to 5, but we're counting from 0 to 4. And so the indices are subtracted by 1. Makes sense. Got that wrong. Bums me out. It's carelessness. 211. This problem illustrates a subtle and interesting. Okay. In the case arguments x and y, in this case arguments x and y to in-place swap both point to the same location. When we compute star x, or star y, we get 0. Then we store 0 in the middle element of the array, and the subsequent steps keep setting the element to 0. We can see that our reasoning in problem 210 implicitly assumed that x and y denote different locations. Simply replace the test in line 4 of reverse array to be first less than last, since there is no need to swap the middle element with itself. Okay. So I got that A one wrong. I'll put star here. Okay, let's go back to here. Where are we at here? We're down here. Okay. One common use of bit level operations is to implement masking operations, where a mask is a bit pattern that indicates a selected set of bits within a word. As an example, the mask all ones has ones for the least significant 8 bits. Indicates the low order byte of a word. The bit level operation X and that yields a value consisting of the least significant byte of X, but where all of the bytes set to 0. For example, with X, there's a bunch of stuff there. The expression would yield just the last 2 nibbles. The expression not 0 would yield a mask of all ones, regardless of the size of the data representation. The same mask can be written as that when the data type int is 32 bits, but it would not be as portable. Okay, practice problem 212, writing C expressions in terms of variable x for the following values. Your code should work for any word size w greater than or equal to 8. For reference, we show the result of evaluating the expression for x, but w is equal to 32. Down here. So we got an A and a B part of this. So and there's a C. Okay. So first part is the least significant byte of X with all other bits set to 0. Okay. X and 0x FF. We just talked about that. All but the least significant byte X complemented with the least significant byte left unchanged. We say X complemented, just complement the whole thing. And then we're going to ampersand that with the negation of 0. That's all ones. We want to do something with 0x FF, and then at the end we want to OR it. So there's going to be 2 operations. The first is going to be to like get the complement set with zeros. And then the next operation will be to OR in the first 2 bytes. So we already have X and 0x FF. So we can then OR that with what I was saying earlier, which is going to be the negation of X ANDed with some value. Oops. And this value is going to be all ones except for the last 2 bytes. So this is going to have to be the negation of 0 to be portable. And then we're going to say, so that's all ones. XOR with 0xFF. So if you take 0, we negate it to be all ones. We XOR with the 0FF. That means those are going to like fall to zeros. And now we have all ones where we want them. And then we AND that together with X, in which case now we have, sorry, negation of X, which means that we have only those bytes, and then we OR it with the original 2 bytes. So there might be a simpler way of like doing this, but that was my intuition. All right, the last one is the least significant byte set to all ones, and all the bytes of X left unchanged. X or with 0xFF. So I think B is probably an easier way of doing this. Let me skim back if there's a complicated. Okay. Okay. If we take X and we XOR it with 0xFF, that's going to give us the inverse of everything, right? Would it? It would give us the inverse for the ones. So let's have a truth table here. So say we have 0, 0, and then 1, 1 for a less. Simplify it. 0, 1, 0, 1 here. The result would be exclusive OR would be 0, 1, and 1, 0. So it inverts. This mask now inverts. So if we take the negation here, I think that would do it. And we'll confirm that in Python. So we take X is going to be 0B 0 1 0 1 0 1 1 0 0. Okay, so that's going to be our X. And then if we do a negation of X, XORed with 0xF, not FF, but F. And then we get the binary representation of that. That's freaking out because it's negative. And it touched these low order bits too. Maybe we can take the negation of the mask. Okay. Cling. I don't see that. Let's do sudo yay install cling. Oh, they don't like doing sudo. That's pretty cool. What is a root project? Oh, it's time to run btop. Go away, please. Can I get a group? Which would be... I just want to create a new group. Move, switch, toggle, window grouping, super G. There we go. So now I can say Command Shift T and put over here Command T. Bam. I think I can apply the negation here. So you say, okay, first byte, and then we're going to negate everything. And then we're going to XOR it with X. Which will invert all the other. So that'll work. I think this one might be more portable though, where you negate everything and then you XOR it with FF. So is XOR like a negation? Let's do a truth table. So 0, 1, sorry. 0 XOR 0, 0, 1 XOR 0, 1, 1. So if this is the original, XOR with a high bit will be a negation. So that's what we're doing here. A negation is effectively an XOR with all ones. I think this would be the most portable way of doing it. Let's see what the book says. So this is 212. They negated the right hand operand, but I think the more portable one would be negate the left hand. I guess it doesn't matter because you know what the size of it will be. Yeah. These expressions are typical of the kind commonly found in performing low-level bit operations. The expression negation of FF creates a mask where the least significant bits are equal to 0 and the rest are equal to 1. Observe that such as a mask will be generated regardless of the word size. By contrast, expression would only work with the data type int is 32 bits. Okay. Makes sense. Cool. Let's continue on with the reading, which is here. Alright, one common use of bit level operations is to implement masking up. We already talked about that. We already did the problem. We are on this page, which is the next problem. Practice problem 213. Digital equipment VAX computer was a very popular machine for the late 1970s until late 1980s. Rather than instructions for Boolean operations and OR, you had instructions BIS, bit set, and BIC, bit clear. Both instructions take a data word X and a mask word M. They generate a result Z consisting of the bits of X modified according to the bits of M. The BIS, bit set, with BIS, the modification involves setting Z to 1 and each bit position where M is 1. With BIC, the modification involves setting Z to 0 at each position where M is 1. To see how these operations relate to the C bit level operations, assume we have functions BIS and BIC implementing the bit set and bit clear operations, and that we want to use these to implement bit functions computing bitwise operations OR, XOR, and XOR without using any other C operations. Fill in the missing code below. Hint, write C expressions for the operations BIS and BIC. So this is 213. Say A and B. All right. I want to reread the first paragraph because I know BIS is bit set and BIC is bit clear. A data word X and a mask word M. They generate a result Z consisting of bits of X modified according to the bits of M. With BIS, the modification involves setting Z to 1 at each position where M is 1. And I guess if M is 0, it just doesn't do anything. So BIS is kind of like a AND. And then, because if M, you're basically X and M. Yeah. And then bit clear, Z to 0 at each bit where is 1. So bit clear is like X and M. This would be X and not M. That's what it seems like it's doing. So then A would be the OR operation. Which BIC is not OR. But you can apply De Morgan's, right? Or an XOR. No, it's not an AND, it's an OR. Bit set is an OR. Sorry, I messed that up. Because bit set is saying, here's a mask. I want all those bits set, and then 0 should only be set if they're in the original. Yeah, so it's definitely an OR. Bit set is like an OR. Bit clear is like an OR with a negation on the M. So OR A would just be BIS of X and Y. So bit clear. Let's do a truth table for bit clear. So we got 0, 1. Oh, I hate this fucking tab completion shit. I didn't even hit tab. It just wants to complete stuff. So bit clear. So if this is M and this is X, so X comes in, we say bit clear, but we only clear where M is equal to 1. Okay. So m is equal to 1 here, so we set these to 0 for sure. And then this is already a 0, and this is a 1. So what I was saying, it's kind of like negating m, we should put a 1 here, and then ORing it with x. Yeah. Negating m, we put a 0 here, and ORing it with x. No, it's not like that at all. It is x. I said x and not m. So let's try that. So not m would be 0. 0 and 0 is 0. 0 and 1, so those are 0. Okay, so not m and gets us the right-hand column. And then left-hand column was to be a 1. 1 and 0, 1 and 1. Yeah. So this is the expression here. X and that. If it was exclusive OR, we would see a 1 here, but we don't see that 1 there. Okay. So how do we implement XOR between X and Y, which would have us have a 1 in this position? That is a good question. Oh, I didn't type in my password, my bad. Please don't have to compile everything again, please. Okay, great. Okay. Cling. Yay. So x is equal to, sorry, int x. Can I do auto x? Auto x is equal to 0 x ff. We'll say f0. Oh, cool. I guess it's C++, so auto definitely works in C++. X, if we say x or, I forget what we're testing up here. Oh, we're testing this stuff. X and 0x ff. Let's say hex representation. Hex. %x, I think it is. Okay. So we got F0 out. So if I do A, B, C, D here, and then I do that, I get CD. If I negate this, I get AB out. Okay. So can I do functions here? Can I say int bis, int x, int y, open, and here return x or y, bis of 0 and 1, 1 and 0, 1 and 1, 0 and 0. Wait a minute. Yeah, I think that's fine. It only had a change on X here, which is what we want. The bis is definitely that. And then I was saying that int bic is int x, int y, and that is return of x ampersand tilde am. Sorry. Y. And then bic. Oops. Bic of 0, 0. Sorry, 0. Why does that not output the result? What can't I fucking call it? Huh? Printf? Maybe because it's 0? I have to have 1 here? I typed a 1. Oh, I typed in the wrong location. Okay, something's wrong with there. I need to restart the interpreter here. Bic, int bic is takes an int x and an int m, and it returns x and not m. Semicolon. It returns fuck. Alright, try this again. Int bic, int x, int m, return x and not m. And then we do bic of 0 and 0. Why does it not print that out? What if I do printf of %d, new line, pound include printf? Sorry, pound include. Standard io.h, and then if I do bic 1, Okay, that's exactly what we would have wanted. But how do we implement, what was this, XOR that we were trying to implement? So bool OR is easy, it's just bit set. Okay. So we're trying to get to what? An XOR, which is a 1 over there. Okay, so if M is a negation, we can say, and we want to OR it together with, so XOR could be expressed as X, OR together with a negation of X, right? Because it'll be X is that true? No, doesn't seem right. I need to do a truth table for it. So say we have, this is the result we want here. If X is 0, 1, then the negation of X is going to be 1, 0. So these will be flipped. So you would have 0, 1, 1, 0. Say you have 0, 1, 0, 1, 1, 0, 1, 0. And you want to get this Y value. This is not it. That would set all ones. So you want it to be X when it's 0, and it's inverse when it's feel like if I was just better at Boolean algebra, it's been a while, I'm kind of rusty on like simplifying algebraic expressions. But we have these two primitives, which is x or m and x and not m. And we're trying to get to an x or. An exclusive or, just using or and potentially negation. So if you pass it through BIC, then we're going to lose a 0 here. And then we have to restore the negation of it, which would be ORing it together with its negation. Can we just get the negation? It says I can only use these two function calls. Damn, this is hard. Maybe I'm misunderstanding what these functions do. So, digital equipment VAX computer was a very popular machine for the last 1970s until late 1980s. From the late 1970s to late 1980s. Rather than instructions for Boolean operators and an OR, it had a BIS set and a BIC clear. Both instructions take a data word X and a mask word M. They generate the result Z consisting of bits X modified according to the bits of M. With BIS, the modification involves setting Z to 1 at each position where M is 1. So that'd be an OR. With BIC, the modification involves setting Z to 0 at each position where M is 1. So you have to negate M and then AND it. So that's the AND and OR. To see how these operations relate to C level so I guess we need to express XOR as a function of ANDs and ORs in order to map them onto BIS and BIC, even though this is an AND with a negation. I don't know how we're going to work through that negation though. So XOR in terms of ANDs and ORs, I'm sure there's some Boolean like rule that I've forgotten for converting between the two. But just looking at the output here, if you take X, you get this column, but then this has to be X and M is equal to X ORed with so we can do the OR, say X or M, which should give us this, and then we have to set this situation where we need to AND it. So that would be this value here. With the negation of I feel like we're making progress here. Negation of X or M, right? Let's try that. So you have this expression, X or M. So they're both 0. So 0, 0, 0, and 1. So that'll be a 0. The 1 and 1, we say 1 or 1 is 1, and 0, 0. And then here we have X is 1, and M is 0. So that's 1, 1 over there, 1 and... So you can never have this situation because anything ANDed with its negation is going to be 0. So if X and M, just say that's a 1, it'd be 1 and 0. If it's 0, it's going to be 0 and 1. So you can't ever do that. So we have this OR to get us that. And then we want to knock out that frickin' value there. We could just do a bis of X and Y, which will give us the value here, which is the OR. And then we need to knock out this bit where they're both ANDed. So if they're both 1s, we want to set that bit. So we're going to have to do a bit clear, sorry. We want to clear the bit, but only where they're both 1s. I mean, if I could do it X and Y here, that would say bit clear. So we're going to bit set to get that. And then bit clear. Bit clear where they're ended? Yeah, where they're ended. But it says that I can't use that. But I can use a bit clear here. Hey, how's it going, 3-1 hack? Bit clear. Trying to figure out this Boolean algebra problem from this book that I'm reading. It's been a while since I've done this Boolean algebra stuff. So if I do a bit clear between X and Y, I don't know. I'm just gonna... Should I cheat? Should I just look up the answer? Feel like I'm struggling on this. This is the truth table that I want for the XOR. I don't speak English, so I can't understand what you're saying unless you write it in chat. That's cool. All right, I'm just going to cheat on this because I don't like this problem. It's pretty close. It's a bis of bic and bic. Oh, because the operand ordering matters? Yeah. Okay. I'm going to read the reasoning here. These problems help you think about the relationship between Boolean operations and typical ways programmers apply masking operations. Here's the code, declarations of functions, yeah. The bis operation is equivalent to the Boolean OR. A bit is set in Z if either this bit is set in X or is set in M. Let's see. On the other hand, bic is equivalent to X and negation to M. So I was able to decipher them. We want the result to equal 1 only when the corresponding bit of X is 1 and of M is 0. Given that we can implement OR with a single test of bis, implement XOR, we take advantage of the property A XOR Y is equal to A and not Y, or not X and Y. Okay. Property. What sort of stuff do you do in Turkey? Or I guess I should ask. Are you located in Turkey or just speak that language? Struggled a bit on B since I forgot the property that X or Y is equal to X and not Y, Y and not X. Okay, next problem is 214. Let's continue reading though. Logical operations in C. C also provides a set of logical operators or, and not, which correspond to the or, and not operations of logic. Makes sense. These can easily be confused with the bit level operations, but their behavior is quite different. Logical operations treat any non-zero argument as representing true and argument 0 as representing false. They return either 1 or 0, indicating a result of either true or false, respectively. Here are some examples of expression evaluation. So we got not 0x41, which is 0, yeah. Yep. 69 and 58. Yep, or 58, yeah. Okay, observe that a bitwise operation will have behavior matching that of its logical counterpart, only in a special case in which the arguments are restricted to 0 or 1. The second important distinction between the logical operators and or versus their bit level counterparts and or is that the logical operators do not evaluate their second argument if the result of the expression can be determined by evaluating the first argument. Thus, for example, the expression a and 5 divided by a will never cause a division by 0, and the expression p and star p plus plus will never cause the dereferencing of a null pointer. Okay, so now we got practice problem 214. Suppose that a and b have byte values 0x55 and 0x46 respectively. Fill in the following table indicating the byte values of the different C expressions. Okay. So I'm just going to go here, mark down table generator. So we're going to need how many columns? You got 1, 2, 3, 4. Well, really just 2. So we do table set size is going to be 2 by what? 2 by 8. And then a header. So 9 by 2. Let's go and grab those. So this is going to be expression and value. And then the expressions are going to be A and B. You got A or B. You got the not A or not B. You got A and not B. Different type of negation though. And then here we got A and B. And then we got A or B. Then we got not A or not B. And then we got A and negation B. Okay. Okay, so our A value is 55. A is equal to 0x55. B is equal to It's equal to 0x46, and this will be 0b 55. So it'd be 0, 0, 0, 0, 0, 0, 0, 0. So 5 will be 0, 1, 2, 3, 4, 5. So it'd be 1 here, 1 here. And we can confirm that by getting up here Python. Say bin of 0x55 1010101 1010101. Yep. And then here it can be 0b 46, which would be a 4 and a 2 and just a 4 here. We confirm that by saying 46 here. 1 0 0 0 1 1 0 1 0 0 0 1 1 0. Yep. Okay, so A and B is a bitwise AND. So that's gonna be the value. Does it want it in decimal? Fill in the following table indicating byte values of the different C expressions. So it wants it in probably hexadecimal, I would think. Let's just look at the formatting here. 214. Yeah, it wants byte values. Okay, so it's gonna be 0 1 is a bitwise AND, so 0 0 0 1 0 0. So that'd be a 44. 0x44. Okay, or just use this temporary scratch here. So we got 0 1 0 1 0 1 1 1 0 1 0 1 0 1 1 1. So that's going to be 4 5, and that's going to be 4 5 6 7. So it's going to be 57. Okay, and then we have here a not A or a not B. So basically there's a 0. So it'd be a 1 0 1 1 1 0 1 1. So that's going to be what? B? B? Because bin of 0xbb is 1 0 1 1 1 0 1 1. Yeah. So that'd be BB. And then A and not B. So not B. B is true, so not true would be false. So it'd be 0. So that's going to be 0. That's an easy one. A and B. That's 0 1 because they're both truthy. A or B would be 0 1. Not A or not B would be 0 0. And then A and negation of B. Negation of B is a negative value, which is still non-zero. In 2's complement at least. So I would say it's non-zero, so therefore it's truthy, and A and the truthy would be truthy, so 0 1. Alright, let's test our results here. So problem 214, it says this problem highlights the relationship between bit level Boolean operators and logical operators, and see a common programming errors to use bit level operation when a logical one is intended or vice versa. Is that really that common though? Where are we at here? Here? Yeah. So you got 4457 BB00, yeah. And then 1101. Yep, cool. Got them all right. So next one's 215. So I can delete this. 2.15 dot. And it says using only bit level and logical operators, write a C expression that is equivalent to x is equal to y. In other words, it will return 1 when x and y are equal and 0 otherwise. Good lord. How am I going to do this? So whatever all bit level, and so we have negation, we have, I guess we start with the bit level, and, or XOR, these are all the things we have, and then we have negation here, and, or, I think that's it, right? All bitwise and logical operators in C. And or XOR negation. And or XOR negation. I guess you have left shift and right shift. I don't think they would consider those for this. And or, it's funny, got messed up and not. Yeah, okay. Using only bit level and logical operators written, write a C expression that is equivalent to x is equal to y. So you're trying to get 0 and 1. This is going to be tough. Let's take it with a 2-bit 2-bit table here. So we're going to say x, y, and then we say x is equal to y. And then here, I'm going to say x is going to be 2 bits. So we just do zeros here. Y is going to be 2 bits. I think what we need is just set all these to 0. I think we need that, that, and then these are all going to be 1. There we go. And then here the pattern is going to be setting these to 1. then this is going to be setting these to 1. So naturally, 2 to the power of 4 is going to be 16. So we have 16 permutations. Okay. And then we're going to need our outputs, which is going to be x is equal to y. So this is going to be true here, which would be 0, 1. Everything else here we got 0, 1. Here we got a 0, 1. And then here we got a 0, 1. Oh, that's that one up. Okay. Okay, so that's our table. These are the available operators we have. So I guess one observation is that we can always get this into 0 and 1. If we have it at 0 and values greater than 1, we could just do the double naught in front of it to get it down to 1. And because of that, I think we can simplify the problem space a little bit by taking it down to 1 bit. Because if it works with 1 bit, it should work with more than 1 bit. If we just apply the same thing to all the bits, right? Because 1 would show up well, yeah, let's go ahead and try taking on the 1 bit example first, which is a lot simpler. So that's just 4 values here. So you have 0 and 1. There we go. And then we'll have a 1 bit value here. And then these need to be 1s here. Sorry, this needs to be X out, and that'll be a 1 here. So the observation here is that it's the opposite. It's the negation of an exclusive OR. So if we go here and we say X exclusive OR Y, that'll give us the bit pattern of 0, 1, 1, 0. Okay, and then the negation, which would be bitwise negation of x, XOR y, that would then be, oops, our value. So that'd be a 1, 0, 0, 1. So what we're looking for. Okay. So you know on a single bit, we can do this. Now, what happens if we take this and we apply it to multiple bits? It's a 2-bit situation. And if it generalizes to 2 bits, then we'll be able to generalize it to n bits. So I'm just going to write def E takes an x and y and returns the negation of x, XOR y. The problem is that Python's thing is like messed up. I think I just do it in my head faster. Okay, so because these are effectively equal. So is 0 equal to 0? Yes. So then that's going to be 1. 1, 1. And then we got 0 is equal to 1. And then we got 0, that's a 0. And then here we got 0, 1. And here we got 0, 0. And here we got 1, 0, 1, 1. And then I'm starting to make an observation here, but I want to continue the table first. So the observation is that wherever there's a 1, 1, that's when we're equal here. So if you do 1, 1, then we have 0, 0. And then we have 0, 1. And then we have 1, 0. Sorry, that's not right. 1, 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1. It's going to be 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. So it's every situation where we have 1, 1 is where we want to have a 1. So what we can do is we can probably say negate all the bits now. Negating all the bits would give us a 0. And then positive, and then we would negate. Okay, so we're going to negate all the bits, which would take away this whole thing. So let me space this out a little bit here. So we're doing a double negation, which would effectively be a just an XOR. Okay. So what I'm going to do is I'm going to copy this whole thing here and paste it over here. And I'm going to say, okay, let's take away the negation. Oh. Okay, so now we can go over here. Can space this out a little bit more. Oops. Don't do that, please. It's hard reaching over this book. Okay, go away. I really don't want that help to ever show up. It's F1. I just hit it on accident because I'm reaching for escape. Okay, so in here, the exclusive OR would be the double negation, so it'd be 0, 0. I guess we can just go in order. I know it's going to be 0, 1, but it'd be 0, 1, yeah? 1, 0. 1, 1. And this is going to be 0, 1, yeah. This is going to be 1, 1. Just goes into 0, 0. 1, 1, 1, 0. Oops. 1, 0. 1, 1. 0, 0. 0, 1. 1, 1. 1, 0. 0, 1. 0, 0. So wherever we have 0, 0, then we have our thing. So then we can apply a not to this. Instead of a binary not, we apply a, what is this? A logical not. Pretty sure that'll get us there. Okay, so binary not, we turn that to a 1, 0, 1. Binary not of that would be, so these are all going to be zeros. This will be a 0, 1. So my place here 0, 1 would be here, here, and here. I think that's the right expression there. All right, let's check the results. So we are on 215, which is this page here. Wait a minute. 215, we're not on 215. Are we? Thought we were further along. Oh, here we are. Okay, expression is not x, XOR y. That is, x, XOR y will be 0 if and only if every bit of x matches the corresponding bit of y. We then exploit the ability of not to determine whether the word contains any non-zero bits. There is no real reason to use this expression rather than simply writing x is equal to y, but it demonstrates some of the nuances of bit level and logical operations. Oops. Okay, so that was 215. Shift operators in C. C also provides a set of logical operators, or, and not, which correspond to the and or not operators of logic. Haven't we already done this? Yeah, that's the wrong page. Shift operators in C. C also provides a set of shift operators for shifting bit patterns to the left and to the right. For an operand x having bit representation x w-1 to x0, the C expression x left left k yields a value with bit representations w minus k minus 1. Yeah. But it's also modded. That is, x is shifted k bits to the left, dropping the k most significant bits and filling the right end with k zeros. The shift amount should be a value between 0 and w minus 1. Shift operator is associated from left to right, so x jk is equivalent of xjk. There's a corresponding right shift operation written in C as x right shift k, but it has a slightly subtle behavior. Generally, machines support two forms of right shift: arithmetic and logical. Yeah. Logical. A logical right shift fills the left end with k zeros, giving a result so and so. Then the arithmetic fills with whatever the last value was to preserve the sign. A numerical value. An arithmetic effort with 2's complement. An arithmetic right shift fills the left end with k representations of the most significant bit, giving a result so and so. This convention might seem peculiar, but as we'll see, it's useful for operating on signed integer data. As examples, the following table shows the effect of applying the different shift operations to two different values of an 8-bit argument. So you got argument x shifted over to left, shifted over to right. Yep. Makes sense. The italicized digits indicate values that fill the right with left shift or the left with right shift. And observe that all but one entry involves filling with zeros. The exception is the case of shifting so-and-so right arithmetically. Since its most significant bit is 1, it will be used to fill the value, used as the fill value. The C standard does not precisely define which type of right shift should be used with signed numbers. Either arithmetic or logical shift may be used. This unfortunately means that any code assuming one form or the other will potentially encounter portability problems. In practice, however, almost all compiler machine combinations use arithmetic right shifts for signed data, and many programmers assume this to be the case. For unsigned data, on the other hand, right shifts must be logical. In contrast to C, Java has a precise definition of how right shifts should be performed. The expression k, or x right shift k, shifts x arithmetically k positions, while x greater than k shifts it logically. Okay. Different operator. All right, I've been going for 2 hours and 45 minutes. That's a significant amount of time. I was shooting for 3 hours. It's getting close to 5 though. So what I'm gonna do is I'm gonna take a break here. I'm gonna run to the store, get some tasty beverages to motivate me to continue onward. I'm also gonna eat dinner, and I'll probably take a walk. So we'll be back probably around 7 p.m. for another couple hours of this. It is unfortunate I didn't put in a lot of time today. I had time available, I just didn't put it in, which is unfortunate. I guess we can finish this last problem before we take a break here. Hopefully I can do it in less than 15 minutes, because that'll fill up my 3 hours. And it'll also get us to the next major section, which is 2.2, integer representations. So we've been on 2.1, which is information storage. So if we look at our index for the book, is there an index? Yeah, here we go. So we got integer representations, integer arithmetic, floating point, and then we're done with representations for a little while. So let's go ahead and do this last problem, practice problem, which is 216. It says, fill in the table below showing the effects of the different shift operations on single byte quantities. The best way to think about shift operations is to work with binary representations, convert the initial values to binary, perform the shifts, and then convert back to hexadecimal. Each of the answers should be 8 binary digits or 2 hexadecimal digits. Okay, so it's a big table. It's a big table. All right, let's go to Markdown table generator. So we're gonna have 1, 2, 3, 4, 5, 6, 7, 8, and we're gonna have 1, 2, 3, 4, 5, 6, 8 by 6. Table 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. There we go. Generate, copy. And I'll actually type stuff in here because it's actually easier to do that. I think we're gonna have to add one more. Yeah, I think we're gonna have to add one more. Generate. Well, we'll say A bit shift 2, A bit shift 3 to the right, logical, and then we'll have arithmetic A bit shift to the right 3. Then down here we're going to have hexabinary. Hex, bin, hex, bin, hex, bin, hex, bin. Then here we have 0xd4, 0x64, 0x72, and 0x44. Okay. Do that there, put that there. 1, 2, 3. Oops. 4 space 1, 2, 3, 4. There we go. And I'm just going to mark all the bits here zeros, even though it's not true, just to fill it out. Okay. Oh. Well, that 15 minutes just flew by, just freaking generating a table and reading the freaking problem. Time flies, brother. Like, it's insane. All right. Alright, so now we just got to fill everything in. So first convert to binary. So we got 4 here. Sorry. Well, that'd be 9. That'd be 8. 1, 2, 4, 8. A. B, C, oops, D, yeah, that works, D. Here are these, we have 4 here, so that's a 4, and then we have a 4, 5, 6, we have a 2, we have a 4, 5, 6, 7, we have a 4 and a 4 here. So 4, 5, 6, 7, yeah. 2, 4, 5, 6, yeah, okay, B. Okay, so if we bit shift over 2, on this one we're definitely gonna have a 0. I'm gonna mark these as like dot. That's a better one, yeah. Let's just search for 0, 0. And we'll do correct 2L dot dot. That goes through it. Okay. So if we shift left over twice, that'll leave us with zeros here. Because we're going over just twice. 1, 2. Then this would be 0, 1, 0, 1. And that would be a 0 here. And a 0, 1, 0, 1 would be 4, 5. Okay. So if we left shift over here, it'd be the same thing. 0, 0, 0, 0. And then this would be 1, 0, 0, 1. Should be a 0 here and a 8, 9? Yeah, 9. Okay. And then we'll have a 1, 0, 0, 0. These are all going to have zeros here. Along with this, these are all going to be zeros here. Oops. This would be 0, 0, 0. There we go. Okay, so now we got that 1, 0, and this would be 1, 1, 0, 0, which will be an 8 here and a 8. So it'd be f minus 3. So f minus 1 would be D, E, C. C? D, E, F. Yeah, it'd be C. And then we got what here? Bin. Sorry, I gotta do the binary first. So that's gonna be 0, 0. 0, 1, 0, 0. So that's just going to be a 1, 0. Okay. So this logical shift to the right by 3. So that means you lose those. So we can do this column by column. Probably be more effective. So, sorry. If we look at the column here for binary, that's all zeros. Look at the column here, it's going to be 1, 0, 1, 0. The zeros, 1, 0, 0, 1, 1, 0. 0, 1, 1, 0. And then wait a minute, we're shifting right. Yeah, so we should grab them 0, 1, 1, 0. This will just be 1, 1, 1. And then this will be 1, 0, 0, 0. Yep. So that's our binary, our hex. We can do later. Arithmetic's going to be the same except for, like, it's literally going to be the same values except for that first one. I'm just going to have ones filled in. So you put that there, and then these zeros are going to be ones. Alright, and then we can convert the hex here. So 1, 0, 1, 0, I believe is, what, 9? Yeah. 9, 1, 1, 0, 0. What was that? That was C, right? C. So D, E. So it'd be E. And then that is just 8. And then this is going to be 1, 0, 0, 0. And then because these are the same thing, I can use the same hex here. So this will be 0C E 8. But this is going to be totally different. Well, 9 is going to be the same. It's going to be F9. Look at that. Alright, so we've got a table. We're only 6 minutes over our time. Let's just check our hex real quick. So we got 50, 90, C8, 10. That's correct. Logical right shift by 3. I have 1A. 0C, 0E, 08. So 1A. Oh, this is going to be A. Sorry. It's probably my hex encoding, not the binary. Just made a careless mistake there. And then we got FA, EC. Wait, EC? 0E, E9. What the hell? An arithmetic right shift fills the left end of K with K repetitions of the most significant bit, giving a result W minus 1, W minus 2, K. This convention might... I don't understand how you get that, though. So arithmetic... I did hex and binary, so, and they switched to binary hex. Okay, whatever. But here, yeah, we got all the 1 zeros, 1 0, 1 0. We got that one correct. And then ACE 9. How is that 9? This might be another problem with their stupid answer key. Alright, so we have 0x, or we say 0b, 1, 0, 0, 0. That's 8, motherfucker. This is another errata. So I have to add that 184 because 0 B 1 1 1 0 1 0 0 0 in hex. Come on, stop doing this. E8. Okay, I'll come back over here. I'm just going to add a task here. TA. Yeah, there we go. Page 184. No sessions. The hell is this? Perl. Well, page 184. Okay. I'm like 100% sure that they're wrong on that one. But I might be wrong on the arithmetic fill on these. So the right shift binary of this, I don't understand how that. So the number here, which I can use Python to calculate. So the ones that I got wrong, or possibly got wrong, were 0C here. He says it's EC. 0E, and then 0.8. So let's do the right arithmetic shift on 0x 64, which is 100. So 100, position 3. Oh, I can do hex here? Cool. Let's do hex, which is going to be 64. Which is 0C. So I think he might have errata on this as well. Oh, he's taking A. What is A? Oh, and he has X up here. There's just all kinds of errors on this. This is error on his end. So he's shifting from, yeah, these two are wrong. So yeah, X decimal is 0C or 19. Three is 0C, right arithmetic. 3 is 0C. There's no difference. These Carnegie Mellon students, I'm surprised they let this stuff fly. All right, promise I'll take a break here. But there are some asides I want to read before I break. So let's go ahead and do that. Close this thing out. Now let's just read these asides. So by shifting by k for large values of k, for data type consisting of w bits, we should what should be the effect of shifting by some value k is greater than or equal to w? For example, what should the effect of computing the following expression, assuming data type int has w32? Then we left shifted off 32, 36, 40. The C standards carefully avoid stating what should be done in such a case. On many machines, the shift instructions consider only the lower log 2w bits of the shift amount when shifting a W bit value. And so the shift amount is computed as K mod W. For example, with W is equal to 32, the above three shifts would be computed as if they were by amounts 0, 4, and 8 respectively. Yeah, that makes sense. This behavior is not guaranteed for C programs, however, and so shift amounts should be kept less than the word size. Java, on the other hand, specifically requires that shift amounts should be computed in the modular fashion, as we have shown. Operator precedence issues with shift operations. It might be tempting to write the expression 1 shifted by 2 bits plus 3 shifted by 4 bits, tending to mean that. However, in C, the former expression is equivalent to 1. Okay. Since addition and subtraction have higher precedence than shifts, the left to right assistivity rule then causes this to be parenthesized like that, giving the 5 and 12 rather than intended 52. Getting the precedence wrong in C expressions is common source of program errors, and often these are difficult to spot by inspection. When in doubt, put it in parentheses. Run linters, write tests. When in doubt, write tests. That should be the lesson learned there. All right, I'm going to take a break. I will be back in a couple hours, probably around 7. Cool.